Questions about anything? Today I'm going to finish off the course material. Before I do that, I thought I'd mention some hints for one of the problems on the homework 9, which is due tonight. So it involves finding the Fourier transform of something that kind of already looks like a Fourier transform. So there's a couple things to think about here. I told you when you're doing homework, you should use these formulas for the Fourier transform. Let's see, so this is I can change the names of these variables to anything I want. So for example, I could change the s to a t, or I could change the x in the integral to any letter I wanted. It doesn't matter. So usually I like to have an inverse transform that spits out a function of x instead of a function of s. But if you stare at those two formulas for any amount of time, it'll occur to you probably that you could do this. You could, or notice rather, that, let's see, if I take the inverse transform of something and I replace the variable by minus, I put a minus s here, then when I write that all out, that's 1 over the square root of 2 pi. I get exactly the Fourier transform that way. So the inverse transform and the regular transform, so I'd have here I minus sx dx, and that's the Fourier transform of f at s. Okay, so that's nice to know. So that it's kind of like they're not really different operators at all. They're just kind of reflections of each other. Anyway, the problem in the homework is to find the Fourier transform of, I think it's 2 over pi, integral from 0 to infinity, which is weird, of cosine sx over s squared plus 1 dx. I think that's it. Well, notice that both the functions in that thing are even. Cosine is even, and s squared plus 1 is even. And so this is equal to an integral from minus infinity to infinity of cosine sx over s squared plus 1. Now that's looking like a cosine transform. But, right. So that's a function of s when I integrate that. And let's see, if you stare at it, you realize, oh, that's the real part of e to the I minus isx. So when you start thinking about it, cosine sx is equal to the real part of e to the minus I sx. And the sine, that would be cosine sx plus sine I sine of minus sx, which is minus sine of sx. And sine of sx is an odd function. So if you think about playing around with that fact, you can write that thing as equal to the actual Fourier transform. So you play around. With even and odd functions, and you would get that this thing is equal to some constant times the Fourier transform of some function g at s. And if I were to have to apply the Fourier transform again to that thing, so I'm supposed to find the Fourier transform of that function of s. And so you think some more. I want to apply the Fourier transform. Let's call this capital G. The Fourier transform of capital G at S, or let's see, yeah, I have an S there. Maybe I should make it at X. The Fourier transform of G at X is equal to the inverse Fourier transform of G at minus X. And now if I were to think about it like that, I would realize, aha, when I hit it with this, I can use the fact that the inverse transform of the transform is the identity. So it's going to spit out the answer. And it's not going to be an integral, it's going to be a function. Okay, so I think I gave you all the hints you need to do that. Any questions about that? Well, I wanted to finish off next the discussion from last time about the vibrating circular drum problem. And so this is from last time. I set it up. I wrote the wave equation in polar coordinates and realized if it's a vibrating membrane, it's supposed to be stretched tight so that the vibrations are small. Then the wave equation is a valid modeling of that behavior, and U is the displacement of the membrane from flat. So it's a measure in the direction perpendicular to the plane. Okay, so I write it in polar coordinates. I realize that there's some boundary conditions. It's being held down on the rim, that green rim at circle of radius 1, and so when the radius is 1 and theta and t vary, that has to be 0. So it's not moving on the rim. And the initial conditions, I know the shape at time 0, and if I hit it with a stick, that would give it a velocity at time 0 also, and I need to know both those things. So if I plucked the membrane, which would be kind of a weird thing to do, then I could make the G be 0 and just have an initial position. But normally with a drum, you whack it with something. So those are given functions, the f and the g. I took c to be 1, so I won't have to keep dropping it from my equations. And there it is, the wave equation in polar coordinates. I did separation of variables and plugged it into the PDE and played around and I could get a function of t all by itself on one side. And so I pulled all the t functions to one side and all the rest to the other. And then the same kind of reasoning we've done in the past, I fixed t and realized, okay, that thing on the right is a constant. And then once I know the thing on the right is a constant, I let t vary again and see that the function on the left of t is the same constant. Okay, I called that constant lambda. Then I have a t problem, which I saved for last. That's an easy one. And then I have the rest of the stuff to look at. I look at that for a while and realize, oh, now I can pull all the r functions and the theta functions apart. Let's see, that r squared in the denominator in front of the theta double prime over theta is annoying. First I multiply through by r squared. Then I can pull all the r's to one side and all the thetas to the other. Then once again I look at those two things and realize to have a function of r equal to a function of theta, they both have to be a constant. And I call that constant mu. And the theta problem then is someone we're familiar with. Let's see. There's the theta problem I wrote last time. For there to be no kinks or rips in the drumhead, I would need theta of 0 to be equal to theta of 2 pi. That would be no rips. Otherwise, it would be ripped along that thing. And also, for there to be no kinks, I would need the derivatives to match up. So theta prime at 0 needs to hook up with theta prime at 2 pi. Those are the famous periodic boundary conditions. And we've done it before, and that's how we get the mu's. The mu's have to be equal to n squared. And the thetas are we get a bunch of thetas, the basis for Fourier series. The thetas equal the Fourier basis functions. Cosine nx, cosine n theta, sine n theta, and 1. Okay. So now that I know what the mu's are going to be, this is what I didn't do last time. I'm catching up to where I finished off. Now I'm going to replace this mu. I know they're equal to n squared. And that's the Bessel equation of order n. So that's adding that n there, that gives me the Bessel equation of order n. And there's kind of a hidden boundary condition for the r problem, namely that r of 0 needs to be finite. Otherwise, the drum would explode at the origin. I guess this is called the Bessel equation of order n after scaling the r variable. But I'm not going to worry about that technical point. After scaling the r variable a little bit. Then it would be the genuine Bessel function of order n that Bessel studied. Well, an interesting case is the case n equals 0. I'm not going to get carried away with these interesting cases, but I wanted you to see where the zeros of the Bessel function come from and where they show up in practice. So, the interesting case is the n equals 0 case. Then it's a Bessel function of order, let's see. This is, there's a famous thing called J0 of x is a Bessel function of the first kind of order 0. So this is, and they used to publish books, tables of values for these things. Just like trig, they used to publish trig. In the back of every math book, you could find tables of trig functions in the old days. now you've got your phone and you can use your calculator to get these things. And the Bessel functions are well handled by the standard software like Maple, MATLAB, etc. So there's no table books anymore. But let's see, this is the Bessel function of the first kind of order 0. That sounds pretty wild. So it's the Bessel function of the first kind of order 0. It solves that ODE with sticking in n equals 0. Okay, it turns out to be the one that's the solution to that problem that's bounded. The one of the second kind is usually called y0 of x is the Bessel function of the order of the second kind. And it's not bounded. It blows up at 0. This is known as that r equals 0, the origin is a singular point of that differential equation. And it's a special kind of singular point called a regular singular point. And that's why we have one solution here that blows up and the other one that doesn't, because of that special nature of that singularity. So that's the Bessel function of the second kind. And it is not bounded. It blows up. So we can toss that solution. It blows up at x equals 0. We discard it. So C1, we discard that solution. We don't want it. And so a thing to note is that C1 times J naught plus C2 times Y naught is the general solution. And so we don't want the one that blows up, so we discard it. Okay. What's happening here? Stupid thing. Oops, sorry about that. What the heck? Okay, sorry. Yeah, and I should mention that I'm using x's now, but r equals 0 is what's called a regular singular point. And so it means the ODE can be solved with power series in kind of a clever way. So it's a regular singular point of Bessel's equation, which is an ODE. So those are words. And so we get this function J naught. And if you graph it, here's how it looks. It looks even better than the cosine function. It wiggles, but it also decays rather rapidly. So let's see, it wiggles. It doesn't wiggle periodically. It gets close to being periodic for big T, or X rather. And it has zeros. And so we call this lambda 1, lambda 2, lambda 3. And it decays, and those lambdas aren't regularly spaced. Eventually they get asymptotically regularly spaced. That's kind of interesting. And those are going to turn out to be natural frequencies of the vibrations. So those are the pitches that you hear when you whack a circular drum. They're different than the pitches that you hear when you whack a square drum. That's interesting. And they're not particularly beautiful to listen to. So drums, even circular ones, don't really make a pretty sound. That's why timpanis have that volume of air underneath. That forces the drum to vibrate in a musical sound with a pitch that's pleasant to hear, almost. That's why they make kettle drums. And analyzing that kind of problem it's going to end up with basically the same as the vibrating string problem, because it has overtones like that. But that would be interesting to figure out, why they make kettle drums shaped like parabolas. Okay, so the fascinating thing about solving these classic ODEs with regular singular points is you can use power series techniques to get the solutions. And so you plug a power series into the ODE, collect coefficients, and it's like doing the method of undetermined coefficients, except this time you have a power series instead of a polynomial. And when you do play that game, you can determine the coefficients of a solution. Now let's see, you get x squared over 2 squared plus x to the 4th, they alternate, over 2 squared times 4 squared minus x to the 6th over 2 squared times 4 squared times 6 squared. Those things in the denominator are blowing up even worse than n factorial. In fact, it's 2n factorial. What is it? I could think about it. I don't know what it is. 2. I could write that in terms of some n factorial if I wanted to. Anyway, they converge extremely rapidly, and it converges even faster than the exponential function and the sines and cosines. Converges faster than the series for e to the x and sine and cosine. And the radius of convergence is also infinite. So these are very easy to analyze, well understood and easy to analyze. And there's formulas for them. And so they're every bit as good as the sines and cosines to deal with. You can numerically compute those zeros to high accuracy. So you find it by plugging summation Cn x to the n as n goes from 0 to infinity in the ODE, and collecting coefficients and doing sort of a recursion thing, which feels like doing the method of undetermined coefficients. So you collect coefficients and recursively determine the coefficients. It's a fun skill to learn. We used to teach it in Math 262 in the old days, toward the end. And recursively solving for them. Well, all of those Bessel functions have that very similar behavior. They've got zeros that matter, and they wiggle. So what you get when you do that, let's see, we've got an n. I'm going to call those zeros lambda 0m for those zeros of J0 and order them getting bigger to the right for zeros of J0. And then when we repeat this process for all the other values of n, we're going to get, let's see, so this, I want to call it R0 of R. Let's see. I haven't thought about this yet, but now I want to think about the boundary condition. And now I'm going to stop writing X and start writing R again. So I'll have R0 of R is the jth Bessel function. Oh, I haven't scaled it yet. Let's see, did I have an M? Yeah, so let's see, I would get, there would be a K here times R. Where K comes from mu. I'm not going to worry about how. So it's like, we could write, maybe it's probably like K squared equals the mu. Or the lambda. K comes from the lambda. So we got to figure out which lambdas are going to work. Okay, so that's the radial thing. We throw away the one of the second kind because it blows up, and so we need the boundary condition. We need R0 of 1 to be equal to 0, and that's equal to J naught of K times 1. We need that equal to 0. And so that's interesting. The K's have to be the zeros of the Bessel function. The K's have to be the zeros of the Bessel function. Of order 0. And so they have something to do with the pitch you hear when you whack a circular drum. Okay, so we get a bunch of solutions this way. Get a bunch of solutions. Namely, I'll call it R, N, M of R would be the jth Bessel function. Let's see. In this case, I'm getting the 0 one. So I get a bunch of solutions, which would be 0m of R would be the 0th Bessel function, and I would multiply by the mth 0. And that would determine what lambdas would work. Okay. And you get a bunch of more when I let the n go loose. From the other ends. And those have Bessel functions of the first kind and second kind too. So those are the really basic ones. Those are the ones that are radially symmetric and there's no theta involvement. So if you ever saw drop a drop in the middle of a cup, then you get these weird waves going out. That's like these. They'd be radially symmetric, kind of like the rings in a pond when you drop a pebble in. But I get even more. I would get an RNM of R. That would be the nth Bessel order n Bessel function, and I would take the mth zero. Multiply by R. By the way, if you play around with Maple and search for Bessel functions, they're all there. So you could write formulas for these things. And a fascinating thing, after you've done the Sturm-Liouville's problem for 10 to 15 different cases, and then you start thinking about the singular version, there's Sturm-Liouville problems for singular ODEs. And when you analyze it, you can see that the RNMs are orthogonal on the interval from 0 to 1, but with respect to a weight function. So they're orthogonal with respect to integral from 0 to 1 of u of r times v of r, and the weight function is r dr, which is familiar if you do polar coordinates, r dr d theta. And the whole theory works like Fourier series. And the first time I encountered this was if you ever look at the famous book by Boyce and DePrima on ODEs, it's in the last couple of chapters. In the old days at Michigan, there was a second course in ODEs where we had to study these things. The whole theory works just like Fourier series. Classic Fourier series. And so you get a solution to the vibrating circular drum that looks like this. U of r theta t equals, the type of the Bessel functions are going to go from 0 to infinity, and then the trig functions you get from the let's see, I'm going to go from from 1 to infinity. And then I'm going to get ANM, the nth Bessel function, and I'll multiply by the lambda nm r cosine n theta. Let's do cosine n theta here. And then the t function turns out to be, so I should go back here. The k, remember? K squared is equal to the lambda. And so when those k's are taken to be the zeros of the Bessel functions, you get one here, cosine lambda NMT. That's the frequency. So that's the note you hear. Those are the frequencies of the vibrations. So those are the actual notes you hear. Unfortunately, that's just the beginning of the... so I'll put here a big bracket. Then the next part would look very similar. Let's see, this part would look like plus. I'll change this A's to B's. I'll change the cosines to sines. Okay. And then I'll do that again. Let's see. Control. Got to add some more. This one I'll need plus. I'll change these to C's. Those are the same. And now I'll go back to cosine n theta. But now I'll make this one be a sine. So you get gobs and gobs of solutions. And you need them all. I'm almost done with the types of solutions. I need another one like this. What happened? Copy, paste. Okay, good. I need this one to be a D. That's going to be the same. And this one's going to be a sine. If I just plucked it, I wouldn't need all of these. But if I pluck it and whack it, and hit it with a stick, then I need all four of these things in all possible combinations. And there'd be formulas for those coefficients involving the orthogonality of the J's. Yeah. Anyway, it's interesting. You want to know what are the, say, modes of oscillation of a circular drum. There's lots of them. Every one of those basic things would be a mode of oscillation. So if you ever set your coffee cup on a vibrating thing, like it's humming at some frequency, every now and then, if it's just the right frequency, standing waves develop in your coffee cup. And that beautiful pattern of standing waves is exactly one of these modes of oscillation. And so they actually have physical meaning, and they happen in nature. They're the standing waves of the circular vibrating drum head. And all the basic motion of the system would be sums of modes of oscillation, just like in the simple string. But it's considerably more complicated. But those functions are determined by hard work. Questions about anything? Yeah, if you ever want to read about this, I like the book by Boyce and DePrima in the later chapters. I think it's pretty readable. So... the last chapter. 2 chapters. Well, it's amazing. I mean, of course, there's hundreds of years where people were working on this and writing papers and books, and it was getting used by scientists and engineers. You might ask about what happens in 3 dimensions. See, for example, you could do the heat equation in in a cannonball, a metal ball. Heat equation in a metal ball. Then, naturally, since it's a ball, you would use spherical coordinates. Which are different than polar coordinates. And then the ODE, and then you do separation of variables. And then the ODE in the R function, for the R of R function. You'd have two theta, you'd have a theta and a psi, but then you'd have a radius. So, or maybe we could call it rho of rho. In spherical, often it's rho instead of R. So the ODE for the, we'll call it R of rho problem, is the Legendre problem, which is also a regular singular point at the origin. It's the Legendre equation. And that's where the Legendre equation comes up and why it's so important. It's a second order ODE. And the amazing thing is, you can do the same theory for the Legendre equation, and you get orthogonal functions that way, which are called the Legendre polynomials. And they come up all over the place in physics and engineering. So Bessel functions are not polynomials, but the Legendre things are polynomials. So that very often you heard that principle that the wave equation is significantly different in even and odd dimensions. Well, the Bessel functions are way different than the Legendre functions because the Legendre orthogonal functions turn out to be polynomials. So in some sense, they're even nicer to look at. Any last minute questions about anything? That kind of brings me to the end. I'm not going to go into the details, but just invite you to maybe look into that. And you might, if you do something more advanced in this area, especially in physics, you'll run into these functions and have to learn more about them. Maybe even learn more about ODE and solving at a regular singular point. If I whacked a bowling ball with a stick and let it ring like a ball, I could be solving the wave equation in a ball also. And that would give me Legendre polynomials. Any questions about homework questions or anything? Need help with? I gave a big hint about the... so it's a famous theorem. If F is C1 smooth on minus pi to pi, then the Fourier coefficients for F are absolutely summable. The Fourier coefficients for F are absolutely summable. Meaning that the sum of the CNs, the modulus, is less than infinity. So a homework hint for that, and that's the Stein problem. The homework hint is you let your f, that would have a Fourier series, sum as n goes from minus infinity to infinity of Cn e to the I n x. And we learned by integration by parts that the Fourier series for the derivative is basically what you get by differentiation. Would be I n C n e to the I n x. And that's this, since f prime is continuous, since it's C1 smooth, f prime continuous, I would have a Parseval's identity. Which would tell me that, Parseval's. That would tell me that the sum of n squared Cn squared is equal to an integral. I think there's a 1 over pi somewhere. Maybe a 1, is it 1 over pi? Of f prime squared. So that would be finite. And that's the key to figuring out this thing. Good grief. Sorry. F prime squared dx. And that's the key to getting this result. So if I were to take an inner product, let's say I would take let's see, I'd make a vector out of, I want to look at this vector, Cn. That's a vector of things. And I want to write that as n times 1 over n Cn. And I realized that that's kind of like a dot product. That would be like the vectors n dotted, that would be the vectors 1 over n dotted with the vectors ncn. Yeah, and now I would use the Cauchy-Schwarz. So let's see. Yeah, these are all positives. So this would be less than or equal to, by Cauchy-Schwarz, this one would be a sum of 1 over n squared, and it would go from it would be 2 times the usual, from 1 to infinity. And this one would be the thing that you get from Parseval's for the f prime. They're going from -1 to minus infinity and 1 to plus infinity. So there's 2. But the only thing is, you think, oh, ouch, I need to make I need to toss C naught. So careful. Toss.